Hey guys, Mr. Betts here. I want to talk to you about something called interval of convergence and radius of convergence. And to do that, I want to start with talking about something called a power series. What I have here is kind of a formal definition of a power series, but I think it's more helpful to look at an example. An example of a power series is what I have at the bottom here, and it's essentially a series, but it's a series where we have essentially a polynomial. So we have x to the 0 power. Now we don't have an x to the 0 power in the example, but it could start at x to the 0, x to the first, x to the second, x cubed, x to the fourth. And in a power series, this is going to go on forever. So we're going to have infinitely many terms. So x to the millionth power, x to the infinite power. Obviously, that's not going to be a specific term, but it's going to keep going forever. So it's going to be in this form where it's going to be something times x to the nth power, or we might have x minus something, and that's going to, remember, if we do x minus r, that's going to shift it to the right r units. So we might be shifting it a little bit, but the idea is it's essentially an infinite polynomial. So when we have a power series like that, what we can do is we can plug in a variety of values for x. And when we plug in a value for x, we're going to get a specific series, a numeric series that may converge or diverge. And we've talked about ways we can test to see if a series is going to converge or diverge, or even converge conditionally versus absolutely. So I just want to look at a couple examples with this particular power series. So if we say x equals 4, essentially what we're doing is we're plugging 4 in for x into the series here, and we get a series that looks like this. So it's going to be 4 minus 16 halves plus 64 over 3, and so on. And we can test whether or not this series converges or diverges using a test that we've looked at before. We could actually do the nth term test for divergence on this one. We could also do the ratio test. So the ratio test is, I think, a little bit easier to use on this one. It's easier to see why it diverges, and we'll go through what the ratio test looks like in a later example in this topic. If we plug in x equals 1, we get another series. Notice that when we plug in x equals 1, we actually get the alternating harmonic series, which we know from before that converges conditionally. So when x equals 4, the series is going to diverge. When x equals 1, it's going to converge conditionally. If we plugged in 1/2 for x, then we get a series that converges absolutely by the ratio test. So I just chose 3 x values. We could plug in any x value we want, and then once we get a series, we can check to see if that series is going to converge or diverge. So let's jump to what the interval of convergence means. So if we take those values that we got there and we look at whether it converges or diverges at each number, so x equals 4, x equals 1, x equals 1/2, I don't care if it converges absolutely or conditionally. I just care if it converges at this point. So we had convergent series at 1 and 1/2. So I'm going to plot those here. 1, we had 1, 1/2, we had a convergent series. X equals 4, we had a divergent series. And we could plug in other x values. So for example, if we plug in x equals -1, we actually get the harmonic series, but negative values. So -1, minus 1/2, minus 1/3, minus 1/4. And we know the harmonic series diverges. So that would not be included. If we plug in 0, we get 0 plus 0 plus 0 plus 0. We know that's going to converge. If we plug in a number like -2, that ends up diverging. If we plug in -3/4, that's going to converge. And if we plug in 1.5, that's going to diverge. If we plug in 1.00000001, that's going to diverge. And it turns out that we get convergent series on a particular interval. So I'm going to clean this up here a little bit. It did not converge at x equals -1, but it's going to converge for values to the right of that. It does converge at 1, and it converges for every value in between. So this is something that we saw back in Algebra 1. This is just an interval. And we can write this in interval notation a couple of different ways. We can use an inequality and say for values greater than -1 and less than or equal to 1, this series converges. Or we could say on the interval from -1 to 1, open on the left, close on the right, this is going to converge. So an interval of convergence just tells us what is the interval of x values that we can plug into a power series to make that series converge. And any power series, we can do the same thing. We can plot the points on a number line. Now, we're not going to do it that way. We're going to come up with another way to do this, but we can plot points on a number line and see where it's going to converge or diverge. And not surprisingly, where the series is going to converge is going to be x values that are all right next to each other on an interval. So an interval of convergence is just the interval of x values for which the series converges. And I mentioned this earlier, we don't really care when we're talking about interval of convergence whether it converges absolutely or conditionally. If it converges either way, absolutely or conditionally, we will include it in our interval of convergence. So if we look at the one that we had an interval of convergence that was from -1 to 1, including the positive one. That would be an interval of convergence. If a power series has x values for which the series converges, there's two things that could happen. It could converge on an interval, like what we just saw, or it could converge at a single point. So this power series right here, there's only one x value that it will converge, and that's going to be when x equals 0. So if x equals 0, it doesn't matter what n is, every term is going to be 0. So it's going to be 0 plus 0 plus 0, that's going to be 0, that converges. Any other x value that I plug in, let's say 1, if x equals 1, then this series becomes 0 factorial, which is 1, plus 1 factorial, plus 2 factorial, plus 3 factorial, plus 4 factorial. What's that going to be? 24, and so on. And you can see we're adding numbers that are getting bigger and bigger, and that's going to diverge. That's going to happen no matter what we put in for x, unless it's x equals 0. So this one here is an example of one that converges at a single point where x equals 0. So the interval of convergence here is actually 0. It doesn't have an interval of convergence. It's just at a single point. So a radius of convergence, radius we've defined before in terms of a circle. Remember, the radius of a circle is the distance from the center of a circle to any point on the circle. The radius of convergence is the distance from the center of an interval of convergence. Call that, say, C. So it's the distance from the center to either endpoint. And it doesn't matter if the endpoint is an open point or a closed point. That is going to be the radius of convergence. Radius of convergence can be useful to us, and we'll see why in some of the examples later. It's easier to find than the interval of convergence using the methods that we're going to use to determine the interval or radius of convergence. So I want to look back at this here real quick, and before we talk about how we're going to find an interval of convergence or find the radius of convergence, I want to point out that for 2 out of the 3 of these, I used the ratio test. And if you remember the ratio test is conclusive in most cases. So the ratio test gives us a method for finding some value called r. So it's the limit as n approaches infinity of the n plus first term divided by the nth term. It looks at whether the series behaves like a geometric series. And if r is less than 1, we know the series converges. If r is greater than 1, then the series is going to diverge. And so the only time we don't know with the ratio test whether a series converges or diverges is when r equals 1, which is, so in most cases, for most x values, we're going to get a conclusion. So because of that, because the ratio test works for so many different cases, we're going to use the ratio test to find the interval of convergence. So the process that we're going to take is we're going to apply the ratio test to the power series. Now, before, when we used the ratio test, we used it for a specific numeric series. Now we're going to use it with a series that has x in it. So what we're going to end up with for r is going to be an expression in terms of x. So we might get something that looks like r equals the absolute value of, say, x minus 1 over 5. And what we're going to do then is we're going to look at where that is less than 1. We solve that inequality. So we multiply both sides by 5. When we have an absolute value inequality for less than, we end up with a inequality that looks like this. and then we add 1 and we get, so this is just a specific example, but you can see here that it gives us an interval. Remember, the ratio test doesn't work when r equals 1, and when r is equal to 1 is going to be at our endpoints. So for our endpoints, we're going to use another convergence test. So if I go back to the examples I used here earlier, for 2 of them, I use a ratio test. For a third one, this is going to be at one of our endpoints, I use the alternating harmonic series. And actually at the endpoint of, at the other endpoint at x equals -1, it was the harmonic series. So we couldn't use the ratio test there, so we're using other things at the endpoints. So most of these tests we've seen before. I shouldn't say most. Some of the tests we've seen before. Some of them we'll be looking at in the future. But we're going to use another test besides the ratio test to see what's happening at the endpoints and to see whether or not we should include them in our interval of convergence. Now, I mentioned the radius of convergence is easier to find. Again, we're going to use the ratio test, but once we do the ratio test, we actually get the radius of convergence. And the reason it's easier is because we don't really care what's happening at the endpoints, so we don't have to test endpoints. We just want to see how big the interval is going to be. So if I go back and use this example right here, I'm going to write that out again. If we get this into the form x minus k is less than r, absolute value, x minus 1 is less than 5, then what this tells me is that the radius is going to be 5. So the important thing here is this is an x to the first power. X is not multiplied or divided by anything. So this is just a 1x right here. Then this number is going to give us the radius of convergence. And if we go back and look at the interval of convergence we got here, this has a size of 10, going from -4 to 6. So half of 10, half of the diameter of convergence is going to be 5, which is the radius of convergence. So to find the radius of convergence, we're again going to use a ratio test. But then once we get this inequality right here, we can stop, and this value is going to give us the radius of convergence.